Last week, we talked about kind of number one on this chart. We really introduced Polymagnet. We talked about their unique design capabilities, kind of the technology behind Polymagnets, kind of a primer on kind of Polymagnet 101. This week, what we're going to do is we're going to kind of change topics and we're going to move all the way into the lower right-hand quadrant. And we're going to talk about this unsurpassed speed and the cost advantage during design and prototyping with polymagnets that they have over any other traditional magnetic technology. Um, so to begin with that, I'll give you my perspective, and Melissa kind of teed you up. My career has kind of spanned, three basic industries, automobile industry, the semiconductor capital equipment industry, and consumer products. And in all of these areas, design is an essential component. And how quickly you can iterate designing and get to that optimum design is really at the center of creating great products. But all designers face this tyranny of the or, and we've been talking about this. I can tell you, I've got a lot of gray hair, and I can tell you that we would talk about this decades ago about, we want something fast, we want something cheap, and we want something high quality. And an engineer would always say, I can give you two out of three, but I can't give you all three of them. And this tyranny of the or has been in front of us for a very long time. We can either get stuff fast, but it's low quality, or we can get it fast, but it's expensive. We can get it high quality and low cost, but it takes forever. Um, and we, and when you think about the design process, that then either slows down the design process, which is a real problem in our, very quick iteration and fast commercialization timeframes that we have these days. Or what we end up with is parts in the development of our product that don't actually provide the real function that we're looking for. And in magnetics, we find this a lot. We find this in magnetics where people will kind of compromise a prototype, but because it's compromised, when they actually put it in the prototype, they're not happy with either the tactile feel of it, the performance of it. Perhaps the weight is higher than what they're really looking for. There's too much variability sample to sample. And many times we see magnetic programs fail because they aren't able to create these high quality prototypes very rapidly. And there's a variety of reasons why this is true. First of all, in the design world, the knowledge of multipole magnets is not well distributed. Uh, Melissa and I were lucky enough to be on the line with a customer at a huge, Fortune 500 company this morning, responsible for design of advanced products. And the first thing he admitted to us, man, I don't know very much about magnets. I know there's a North Pole and a South Pole. And, I would have to say that it's very rare that we actually find engineers responsible for designing components or subassemblies, which include magnets, that really have a deep understanding of magnetic technology. And then beyond that, an understanding of advanced multipole magnets and how they work. By nature, we lack off-the-shelf components. They're just generally we're creating very unique, complex patterns. So it's not like you're going to go into a catalog and find exactly what you need. We lack the advanced design software to create these functionalities, or at least we have until we launched Polyvision just this last year. So now at least design engineers can have access to advanced design software for multipole magnets. Prototyping of multiple magnets, if they're really fine and intricate patterns, it's almost impossible to prototype with any other, non-polymagnet magnetizing process. For those that are perhaps simpler, you might be able to magnetize, but it can either take a long time. Again, this week we talked to a customer that was quoted over 6 months and $50,000 just to get a prototype, and the company warned it may not work. And he was kind of sitting there going, well, what do I do now? I don't want to wait 6 months. I don't want to spend $50,000. I have no guarantee that this is even going to provide me the full saturation and the pattern that I'm looking for. That's just a really tough conundrum from a design perspective. We've also seen the last happen, and that is settling for close enough, where because prototyping is expensive and takes a long time, uh, we don't actually optimize to perfection. We get the first sample back, Nobody's really thrilled with it. It doesn't really give us what we are looking for, but we're not willing to go through another iteration. So we either go into production with that, constantly kind of unhappy about it, or we abandon it and we go after some kind of mechanical solution or something that's not magnetically related whatsoever. So there are a series of significant and real barriers for us to be able to solve this tyranny of the ore. Now, in all fair disclosure, I got my design background serendipitously. I was at a conference in Europe early in my career and met Thomas Gerlach. And Thomas Gerlach was one of the founders of Frog Design. Frog Design was the agency that actually designed all of the early Apple products. So they designed the first Macintosh and the mouse, and all of the products that we kind of grew to love, and really created a design ethos in Apple. And today, of course, Apple is, everybody I think believes that they're kind of the paragon in optimized design, of not compromising, of creating designs that truly are perfect. They iterate until it feels right, smells right, uh, you know, sounds right, functions right. That there's no compromise when they launch a product into the market. A lot of that was driven by Frog Design and Thomas Gerlach, and I had the opportunity of working with him and learning from him. So I kind of got my background there. Apple and Johnny Ive certainly has taken that to all incredible new levels. And what's happened though is because they have used magnetics for haptic field precision, function alignment, material reduction, all kinds of different things. Other companies now have come along and begun to follow suit. I think everybody wants to be Apple. Yeah, I think that's a pretty standard reply of they'd love the margins, they'd love the brand, they would love the market share kind of penetration that Apple has. And we have started to see now a whole variety and host of products, worldwide, that really have this kind of same non-compromising design ethos. Whether it's a Nest thermostat, a Dyson fan, Peloton bike, a Yeti cooler, a Harman Kardon speaker, there are dozens of products now that really just work right and feel right, and at the same time harness the magic and the power of magnetics. So I think the market for magnetics is going to grow because of this, but more importantly, the expectations of what a magnet is going to do, how quickly we need to iterate to a design, and how perfect that design actually needs to become. And consumers are not about the less demanding. I think once you experience a Nest thermostat or a Peloton bike or a Dyson fan, it's really hard to go back to a product that's not really designed with compromise, without compromise. So I think there's kind of no going back from this frontier. Once companies like Dyson and Peloton and Yeti and Apple come to the market, they set a new bar. Consumers then adopt that new bar, and we designers now have to live up to their expectations. So Polymagnet really enables the era of and rather than or. We have the ability of fast design where we can print prototypes within hours. We have the ability of designing, home printing within hours with our software and our prototype machines. You can do it incredibly inexpensively because there's no incremental capital. You're not buying some unique capital fixture that you have to throw away later on. You're just taking a base magnet, putting it in the polymagnet process, and digitally magnetizing it. And what you get is high quality. It is produced with exactly the same precision as the volume manufacturing process. So it is the volume manufacturing process. It's not like you're creating some secondary process that doesn't have the same tolerances and doesn't have the same saturation, but it's really fast and cheap, right? Which would be a normal conundrum for a designer. You're using the actual manufacturing process. So the ability to design quickly, print quickly, do it inexpensively, and have it done with the process that you will use actually in production is fundamentally transformative to the area of design and design optimization in incremental design. So, uh, we're going to take you on a journey. And we're going to walk you through kind of a real example so you can see how this works. But we can design advanced multiple magnets for an application in less than a day. In fact, in in a day, not only can you design the magnet, you can prototype the magnet, you can review it with your customer, you can get feedback, you can iterate that design, and you can actually produce your second and even your third design in a single day. And I can tell you we've done that with customers. So this is not something that, oh wait, it's impossible. Maybe if it was super simple. No, if you spend a day with a customer, you can easily, you absolutely can get through one design iteration, and you can easily get through two or even three design iterations with a customer with the polymagnet design and prototyping process. You can create functions and levels of haptic control and performance that are, seemingly unachievable. You can prototype your designs, in less than an hour. You can iterate design changes the same day, as I said. You can produce final prototypes in a day. You can iterate prototypes during your design review meeting, your customer visit. And all of this again with the precision of the manufacturing process and a cost of simply running the machine, which runs on standard household current. This is not even a two-phase or a three-phase machine drawing significant amounts of power. This is a low power, high precision, digitally controlled magnetization process. So seeing is believing. So we're gonna take a little journey today, and we're gonna actually watch. I know we're gonna watch in real time how this really happens. So you're gonna meet an engineer here, and this is one of our engineers. You're gonna meet Steve. He's an engineer with the challenge. Uh, Steve needs to deliver a product concept in prototype form very fast. And he hasn't even met the customer yet. So, he may have talked to the customer on the phone for a half hour to kind of have some idea, but he's going to meet with the customer, get a better understanding of what he's got. He's a pretty busy engineer. He likes to go fast, and he's super impatient. He spends his design time pretty efficiently to get a prototype quickly, and he wants to iterate fast. And I think that is kind of a call to action or a basic principle of almost any successful designer these days. We have to go quickly, we have to work efficiently, and we have to get to a really accurate representation of our ideas quickly. His design process is pretty quick. He gathers requirements and feasibilities. You can do that on the phone. You can do it during your first meeting. He creates some basic specs because of that. He goes through the design process using Polyvision, which is our design software, which you'll see in operation here. Uh, he then will simulate, if applicable. I would say in 90% or more of the cases when we design with customers, we do not even enter into simulation. Simulation is many times done when it's really hard and expensive to create an actual prototype. Or if you're doing something that may be a pattern or a function that you've never seen before, and you're not sure whether or not you can create the appropriate field or forces. In most of our cases with customers, they are doing things similar to what has been done in the past functionally, so you have a high degree of confidence that the function is going to work. And since you can prototype literally in hours, it's better to just move straight forward and make the prototype and move on from there.
It's like that's what most of the customers we work with, they kind of don't feel that need to.
Yeah, I mean,
you can.
we, as you well know, we've had some odd requests for some really unusual projects, and in those cases, simulation works really well. And the nice part is our software produces the step file, which is exported directly into. We happen, to use one specific ANSYS type system, but there's a lot of different magnetic modeling systems out there. And it produces a step file that you can send to a magnetic modeling system, and you can go through simulation.
All right, I'm getting really excited now.
All right. Next state, he wants to go prototype, right? And then you test it, and you can either test it through laboratory characterization, or you can put it in the hands of the customer, and you can just literally test it. And of course, then you got clinicking, and you can kind of move on. So that's Steve's process. So let's just kind of watch. He's going to have his first customer.
That is the look that Steve has on his face.
Yeah, he almost always says that. To what? You want to do what? Anyway, in his initial custom meeting, the specs kind of evolved out of this discussion, and what they were trying to make is an action camera tripod, kind of like a Joby tripod, and then an action camera. Traditionally, these things would be kind of screwed on, but you might have bike gloves on, you might have ski gloves on. It could be cold. If you drop the screw in the dirt or the snow, you could lose it. So they wanted to change this up. They said, let's design a very quick attachment for a camera to a tripod. So magnetically, this thing just snaps right on, automatically aligns, right? There's no adjustment, and it has a really high attachment force, right? So it's not going to fall off, get knocked off. So really high shear strength. And they had some physical constraints of it being less than 2 inches wide, and they wanted to minimize magnetic material. Now, the other thing, by the way, I will say on this is they wanted detents. I forgot to mention that up in there, and that they wanted a 20 detent indexing, right? So, and by detents, we mean as they rotate the camera, there is an obvious kind of position. Every 20, there are 20 of these as they go around 360 degrees where the camera will kind of lock in position. So the camera isn't just free floating and circulating around. It's set in a position, it stays that position, that you can then move it. And you can imagine how important that would be for a camera type system. So this is actually a real-time video, and this is our Polymagnet production software. And you can see that this is kind of the administrative project setup screen. And if you look closely, Steve's typed in a project name. He typed in a few little details over there about the project in that box. This is where you would determine the kind of magnet, the material specification of the magnet. And a lot of these are drop downs, obviously, the material specifications. We have a wide list of neodymium and other materials that are available. There's also a very wide list of geometries of magnets, which are generally available. But if you have a very specific magnet, something very unique, you can simply upload a CAD file at this point as well. So it'll basically create anything that you want. So this is just all about, again, geometry, material, where you're going to store the files, catalog setup. And you can see there the magnet they picked. It's a simple coin magnet with a flat on one side, and the flat is so that as they injection mold that it won't rotate in the injection mold. Once then in the system, Steve likes to say, wow, it's almost like PowerPoint for magnetics. Well, it's not just about PowerPoint and visual issues. And what we're doing is we're dropping around individual maxils, and maxils are areas of magnetic field. So as we digitally print, we print one maxil at a time. So each one of those little teeny circles that you see there is an individual firing of the correlated magnet, of the polymatic magnetizer. And he's kind of playing with a lot of things here. You wouldn't actually have to do all this, but he's kind of showing you the capabilities that you can kind of drag, and as he moves that circle to being bigger and smaller, it automatically calculates the number of macros that you would need. He was kind of playing around just to kind of show you some of that. So that zone in the middle that he created is kind of the high attach zone, because remember the customer said he wanted a really strong attachment. That's great, but he also wanted detents. Now, detents are created by creating a ring of alternating norths and souths. And as you have a pair of magnets with alternating norths and souths, they are going to want to connect at every one of those detents. So for 20 detents, you would need 40 poles, 20 north poles and 20 south poles. And if you do that, the two magnets then will have 20 of these very nice detents. And you can program this to have any kind of feel. So what's the force between detents, et cetera. And then you saw at the very end, it kind of showed you a little bit of 3D model of the finished magnet. And here you can see design time for this thing was about 5 minutes. Now, Steve's obviously very good at this. Let's say it took you an hour. It still only took you an hour to come up with the design based on what a customer needed. Now, where you would go from here, so you started with our Polyvision system, what was anything to 5 minutes, but let's say it's an hour. Say it took you more than 10 times what it took Steve to do. It's still a ridiculously small amount of time to create a sophisticated object. And remember, what you have at this point is you have all the step files now that are ready to do any kind of magnetic simulation. If you wanted to go into magnetic simulation, you have the step files to make the tray that will go in Thinker. And you have the magnetization instructions for the printer to actually go and make this specific movement. So, in a very sophisticated, wild process, you would now move into simulation, or you would go directly into producing the tray. Now, in this case, we would not go into simulation. Uh, Obviously, high attract is something we know a lot about. Detents are something we've done a million times. These are two functions we're very comfortable with. We know exactly how they're going to behave. There would really be no need for us to move into this. But if you wanted to, the files would have been created by Polyvision at this time, and you could move directly into simulation. So the next normal step is you have to have a tray to hold the magnet. Now, if you've ever used this magnet before, you'd already have a tray, so you can skip this step. But in prototype phase, we just use a 3D printer. Steve hates this because our 3D printer is slow. There are way faster 3D printers out there. So it took Steve 50 minutes to sit there and watch this little plastic tray be made. Now, in this case, he made a tray with only one magnet holding position. You could have made a tray with multiple magnet holding positions if you wanted to. So at this point, he's kind of 55 minutes into this thing, but let's be, super liberal. Let's go look at, let's say it takes an hour to design, it takes an hour to print a tray. In 2 hours, you have your design, you have your step files, you could go to simulation, you have a tray to make a prototype magnet. So now you're ready to go. So the magic begins. Here you can see Steve is just taking a standard magnet with a flat on one. He was just testing to know which side is up, north or south. He stuck it in his tray. He's going over to the machine. He's looking for the file on the machine that he has sent to the machine. He picks it. You can see it shows up there on the screen. He goes, "Yep, that's the file I'm looking for." He's just going to take his tray. He's going to set it in the printer, close the door, and he's going to hit the green button and the machine will start. Now, the machine is off for a while, so it's got to just reset for a second, and then it begins printing. It's now beginning to print, and in a couple seconds here, and the printing is now done. So at this point, printing is finished, and that magnet is complete. So, literally, the printing process here, I think, was around 12 seconds or something like that. Steve will show you, he's going to put up some magnetic film paper on this so he can show you that we went from just a regular old north-south magnet to a completely magnetized custom poly magnet for the customer specification. Now he's going to go ahead and print another one because if you remember, this is a solution that requires a pair of magnets. There'll be one magnet on the tripod and another magnet will be in on the camera. So he's going to put that back in and he's just going to repeat the process. The file's already pulled up here. The machine's already going, right? So this will just be a little bit faster in this case. And you can see the little green progress bar goes across. And we haven't sped anything up here. You might go, "Oh, this is a little boring. Why are we watching all this?" I'm doing it actually to demonstrate. It'd be easy for me to speed all this kind of stuff up, 5x the time or something like that. So you would go really fast. This is the real time. So at this point, Steve himself spent 5 minutes on design and another couple of minutes magnetizing two magnets. And his longest time was that he had a 3D printed tray. So in this case, in less than 1 hour, Steve already has the pair of magnets required for a prototype. Now Steve gets crazy. He does all kinds of wild things, right? So he could give these to the customers right now and hand them to them, but he's going to go for gold. So at this point, he is going to actually make the actual device that would screw into the tripod, and because the customer gave him, in this case, CAD drawings. So in this case, you can see what he's done is he's actually already 3D printed the cup, right? He put a little super glue kind of down in there, right? Secure the magnet. He's now going in and he's putting his specially magnetized magnets in each one of those little cups. And he's going to put a little bit of adhesion coating on the top of these so that the plastic material sticks better to that kind of shiny finish. You can see that's what this stick is here. It just helps the plastic material stick to the nickel finish on the batteries. And he's going to go ahead and finish the design there. And again, the 3D printing, we have a pretty slow 3D printer. So this stuff takes probably the most time. But
Maybe for Christmas we could get
if we could
Steve
get
to,
Steve a
yeah,
faster printer, he'd probably think that was the best thing in the world. So this step varies, based on the design and the machine, obviously, that you use, how big the part is. We were actually at a 3D printing company the other day, and they were printing these ginormous 3 foot by 3 foot 3D printed structures. I can only imagine how long it takes to print something like that.
yeah.
But in this case, this took, again, less than an hour. So at this point, you actually have the exact prototype that the customer is looking for. So in less than 2 hours, you are meeting with the customer, you got his specs, you sat down, you used the Polyvision system to create the design, you have the step files for simulation, you have the step files for the tray, you have the step files for production, you printed a tray, you loaded a magnet in the tray, you printed your prototypes, you then went back to your 3D printing machine and put that prototype actually in the customer's actual product, and you're actually ready for customer feedback. In this case, you know,
I must say the acting is incredible.
yeah, there you go.
Yeah.
Yeah, but you can see he even printed on the side how many detents there were, right? That's easy thing to do in the file, right? Uh, Super happy with the amount of attach force, very strong attach force, really great in shear, auto alignment. Uh, you had your 20 detents there. Yep. So, it was, and that exactly what the customer was looking for.
Now,
But
what I find interesting is, Tim has given this talk now at several different magnetic conferences. To me, this seems normal. Like I just am kind of like, of course, this is how you do it. But I think, for most engineers out there, even magnetic experts, this is just completely unheard of.
well, 3D printing has really changed the world of designers.
Right.
Where they can kind of come up with it quickly with a model and say, let's go 3D print it. But when you 3D print it, you're usually printing it in some kind of plastic, some polymer,
Mm-hmm.
and your end product is probably not that polymer. So you
Right.
can get something back that looks like what you're going to want,
Right.
but it's not in aluminum, or it's not in stainless steel, or it's not in nickel, right? So even 3D printers, now there are metal printers and all these other issues, but even a lot of the things that designers do in 3D printers, they're still dealing with the tyranny of the ore.
Yes.
I can get it fast and I can get it cheap, but it's not made of the right material.
Right.
But they go, but that's okay. I can see if it works and blah, 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 blah. In this case, you're actually getting the exact magnetic function
Yes.
with the exact magnetic process that you would use in production.
We do have people really sitting there thinking and looking and going, really? Really? Seriously? You do this?
Especially in the world of magnetics, because like I said, most multi-pole magnets, if they're really sophisticated design, there's really no other way to do it anyway.
Right.
But if you had a fairly simple design, look, you can take little teeny needle magnets and try to glue them all together in a pattern. Oh, it's a disaster. The tolerances aren't the same. The feel isn't the same. They often crack or break.
Misbehave.
Well, they crack and break because
Right.
they're so small, which means you have dead zones. And so by the way, and that's not how you would ever want to do it in production,
Right.
right? So, it is really a breakthrough from
Right.
an advanced magnetics perspective.
Even for, companies or customers who may be contemplating more traditional magnetization, this is a game changer for the whole prototyping world. So you wouldn't even necessarily have to use polymagnet if it's possible to do it traditionally. You wouldn't have to use, uh, that polymagnet in your end product. But
Don't have
for
to.
prototyping,
But what we found, though, is that polymagnet in the production side of the world is also probably the most cost effective and by far the most flexible. The one thing that, again, in our world we forget about is we say, well, here's the product. We're going to go make 1 million of these a year. But what you forget is that in 6 months, you might need to make a small change to it. Either because something else in the product has changed or because there's some customer feedback or whatever. And if you have a bunch of sunk cost, the economics then of purging that sunk cost are tremendous. With polymagnet, it's a file change.
right.
You can change the product with a simple file change and start producing it again. So the lifetime cost of producing magnets with polymagnet is by far much more affordable than any other way.
And I
manufacturing
probably
production.
took it off topic. So anyway,
Anyway, like most customers, you hand them the product that they asked for, and they go, "Oh, this is great. This is fantastic. Good shear force, great attach, exactly what we wanted. Oh, I love the detents." And they go, "Well, it's funny. Could we do 24?" See, and they go, "See, if we do 24, that'd be 15 degrees. That'd be easier, blah, 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 blah." And, usually you're going, "Oh my God, that's another 6 months. What are we going to do about that?" In this case, when the customer goes, "Yeah, we need 24," right? That's a 1 hour revision.
right.
That's literally says, "Why? Sure. Why don't we go to coffee? Why don't you get some lunch? Come back after lunch. I'll have your revision for you."
I'll have your prototype ready.
So
Right.
to kind of review this, you have a customer meeting, you get the spec development down. Now, one of the things you have to do in a customer meeting is make sure they're not violating the laws of physics. They're not creating a perpetual motion machine or something like that. But in general, you try to get the specifications locked down. You then go into Polyvision, the design process. I'll put 5 minutes here, but like I said, Steve's great at this. He knew exactly what he was doing in this case. Let's say it takes you an hour. Let's say it takes 2 hours in design, right? It's still an incredibly fast process to come up with final design. That then spits out all of the files that you need for simulation, trays, and manufacturing. Um, like I said, if you've made anything with the same magnet before, then you don't need a tray because the tray can be used over and over and over again. But if it's your first time, sure, you're going to have to go get yourself a tray. Then you'll go to custom uh, magnetization, which is the fastest part of all of this, is actually putting the pattern in the magnet. And then, prototype production, all in all, less than an hour. Multiply it by 4. Let's say it takes half a day. Let's say it takes you all day to go from meeting the customer to giving them a prototype. It is, a fraction of the time of any other process and a fraction of the cost of any other process. And it gives them the actual production product. Same quality, same tolerances, same capability. So in summary, less than half a day, we went from initial customer meeting to a functional prototype to an optimized design to a final prototype. So
Well, and we've even seen this work. We'll be on Zoom or something with a customer, and Steve will be designing, and then he'll make the prototype and he'll overnight it to the customer for next day. And
yeah, I mean,
that's
I literally have seen this where I, and Steve are on a call with a customer. You're talking to them about a couple different things, and you
right.
may be
We're
talking about,
chatting.
oh, you may be talking about an NDA and blah 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 blah, and Steve's gone silent. And when you stop talking, Steve goes, "Oh, by the way, I think I kind of have a pattern here for you." And he literally pulls up Polyvision and he's already done it.
Right.
And he goes, "Yeah, we may need to tweak this or we may need to tweak that." But
And I got your samples going right now.
but
So
but this is your basic concept. So it is truly phenomenal. So Polyvision, Polymagnet in general gives you, this incredibly unique and superior design functionality, the quickest and lowest cost of prototype and production capabilities. It supports the iterative design, continuous improvement, of the entire product commercialization process that is just required in all industries and utilized by industries today. It increases your IP protection. It's the lowest cost of production assurance that we provide with our Polymagnet promise. And then you have an end-to-end equipment and tool set that is in place to take you from the very initial stages of ideation to full scale, high volume production manufacturing. There's a lot of great brands out there in the world, and we add to this list every single day. We have a whole bunch of new people to add to this list.
And we have a challenge in that a lot of customers would
Don't
like to
like-
they would like to remain anonymous. So
Yeah, we have that too.
but it
And
is
it's
phenomenal.
been recognized by a lot of different entities out there in the world as being, an incredibly innovative product. And with that, I hope all of you will, one, connect with Polymagnet. There's a ton of information out there on our website. You can email us at any time, generally at Polymagnet, by emailing connect@polymagnet.com. You can follow us on LinkedIn, where we post different articles and content. We do have all of these webinars that we post on our website as well. So if you haven't attended a past webinar, you can go back and see other webinars that we have created. And if this is at all interesting to you, we have another one coming up on the 10th of April. We're going to be talking about designing your supply chain for resilience in reducing the use of rare earth materials. So this is a really sensitive subject these days, both with tariffs as well as supply chain availability concerns, as well as national security issues. So we're going to talk about how you can use polymagnet to reduce the amount of rare earth material that you use or completely eliminate it from a design. So that
Right.
should be of interest to some designers out there. And if any of you want to contact directly with me, don't have to put you in polymagnet. Feel free to reach out to me at my email address or call or text me, and you can follow me on Twitter. Yes, I know it's called X now. You can follow me on Twitter, uh, or you can also connect with me on LinkedIn. I'd be more than happy to connect with you as well.
Yeah. And Tim, we have some comments and questions. So,
Awesome.
Jeff Eliason, we didn't even pay him to say that. He said, thanks for the inspiring webinar. I love the emphasis on speed. And for those of you who don't know who Jeff is at MMI,
Polar
and
Star.
Polar Star, he is an amazing partner, and
He
they
is.
are experts in polymagnets as
Yeah,
well.
and
So,
I might mention that we have a super flexible manufacturing system. That's not the topic of this talk.
right.
It'll be a future talk. We'll
Yes.
have Jeff on. That would be a great idea.
Yeah.
But we sell our manufacturing equipment to OEMs. There are certain OEMs that actually want to kind of keep this secret sauce inside of their plant and proprietary and away from anybody else. But we also sell our equipment to major leading high quality manufacturers around the world, Jeff being one of them
Hmm.
with Polar Star. And they have manufacturing capabilities both in the United States for quick support in the US or domestic manufacturing requirements. And then they also have manufacturing capabilities in Asia, in China as well.
Yeah.
So we have a robust supply chain out there when people get ready to move into the
Yeah.
high volume world.
And then we have another question, and what is the cost of entry into these machines?
Yeah.
So a couple of different, different answers to that. One, if you're interested in the design software, we took the software that we've been using for years and years and years and said, why don't we make this available to all, any and all who
And
have
it
interest?
is. It is
And
now
it is
available to
available.
anybody that wants it.
And it's just an annual subscription of $4,900, so very affordable from that perspective. And then we also, as part of, when I think about our philosophy as we kind of stepped into the company, what we realized was we need to affect technology transfer, which
Yep.
means we need to give people the tools and the equipment to kind of self serve and take it as far as they want. At the same time, we're perfectly willing to do professional services and do all of that for a customer.
Yeah.
And they can tap in where they want.
What I like to say is we are happy to do it all for you.
Yep.
We will design it, we will simulate it, model it, we will prototype it, we will characterize it. Uh, we will help you identify supply chain suppliers and get a manufacturing vendor for you. We'll do 100% of that for you, so you don't have to do any of it.
Yeah.
We're also happy for anyone to do that 100% themselves
Yeah.
or any combination therein.
It's a journey,
It's a
right?
journey.
They
Yeah.
step in kind of working with us, and as they get comfortable, then they want their own software and
But
machines. In terms of the prototyping units that we've developed, and that's part of making this available to more, we have a couple different units. We
Mhm.
have a desktop version, which is PolyDesk, and then we have a larger prototyping, which is really meant for labs, maker spaces,
Yeah.
kind of bigger projects, if you will. So those are our product prototyping units, and then we have much bigger production units, which has some variability to it. So we're trying to make that really affordable for companies. I will tell you, universities are going crazy with this, and any company that has kind of an engineer lab space. A lot of the government agencies
I
are going
think the
crazy.
university things I think is it's so fun to me because
Yeah,
it's the PhD student and the professor that first sees it and goes, we have to have this because they have projects that
right.
require this kind of stuff, right? Um, but then you start talking to them and they realize how amazing this would be in the hands of the undergraduate students for all their design classes. You think about it, every university and every engineering university in the country or in the world today has these kind of maker spaces for their design classes to
Right.
make products, but they don't have any way of making magnets.
No.
All they can do is use a simple, dumb north-south magnet. And every university in the world needs a
Yeah.
polymagnet
I mean,
center.
we were over in the UK with Leeds University, and I was just blown away
Well,
with
they're doing some
you're
amazing
into
stuff.
the medical space and the phenomenal work they're doing that will make our lives so much better and save lives. But they really, really, really
Well, they're
big
doing
magnets.
very unique magnetically controlled surgical devices, and you can't do that with simple north-south magnets.
No, they were dumb magnets. So anyway.
Well, I hope everybody enjoyed
I
today.
don't see any more questions popping in, but again, reach out to us anytime. And we love talking magnets. So we'll let you know. Thank you for joining us today. Bye, y'all.